Okay, welcome everybody to this morning. Hope you're enjoying the show. How many are? Of course you're supposed to put your hands up, come on. We're going to talk about air barriers. How many, are you installing air barriers? Do you know what an air barrier is? And if you don't put up your hand, you got a lot of company, because we've been doing this for 22 years and still that's a big question out there. It's still hard to hear me. They said this is maximum. Maybe I can adjust. Is that any better? Still not bad? Okay. I will talk as loud as I can. Anybody know what this is? Groundhog. And the reason why I put that in is for over the last 22 years we've been involved with air barrier installation, and it's like nothing's changed. It's the same day after day. So I started off the presentation, I was going to put all these wonderful pictures of perfectly installed air barriers. And then I decided you guys would go to sleep. So I'm going to show you what not to do, and then I'll give you some guidance of what to do. So I'll go through this quickly. The point I'm trying to make at this slide is, when did we start using air barriers? The short answer is when we had some sort of place to live. So if you go back, the first slide in the upper corner there, that's a really good air barrier. Solid rock does not let air go through. What's wrong with this picture? They did 5 sides. Keep that in mind in your building. There's 6 sides to your building, so you have to have air barriers on the roof and your foundation, not just the walls. And then we go through the different ways, but all of them keep the air out. And even years ago, decades ago, they applied building science. It's kind of hard for you guys to see this, but there's an opening at the bottom where you have snow. Why would you do that? Let's keep the cold out. Well, what did they use to keep themselves warm? A fire inside the teepee. So they're using the buoyancy effect to take the smoke out the top. So we got to do the same thing today. Stack effect in our buildings is a big issue that we want to solve. Here's what happens if you don't do a good job with your air barrier. And this has happened over years. Everybody's seen these type of pictures. And we blame it on a leak in the roof, a leak in a wall, and so on. But a lot of times there's no leak. It's an air barrier problem. So air barriers sometimes are associated with cold climates. Fargo, North Dakota, Chicago. We got to put them there because we got to keep warm. The number one place you should ever have an air barrier is in Miami, where it's 110 degrees and 98% relative humidity, or Houston, Texas, and so on, because it's moisture management that we're dealing with there. And of course, the good old mold pictures, go on Google and you'll see mold coming out all over the place. But this is a southern climate issue in a lot of cases because it's warm, moist air leaking into our walls, condensating on the inside of the interior sheathing, creating mold and so on. And if you're staying in the hotel here and your room kind of is musty, smelly, you know, go to the corner, pull up the vinyl wallpaper, and you're going to see mold. Now, you may have to put pay a damage deposit on your room because you opened up the wall, but you know, it's worth it. And it gets into one project I was on. They were replacing the steel studs and so on, and you're literally taking the steel studs and the tracks out by your hand. It had corroded so bad there. So it can have some pretty major damage out there. And if you've ever been up in your attic and you have a glass fiber type of insulation and it's turning all different colors, black particularly, that's because you got a lot of air leakage there. We use fiberglass in our furnace to take the particles, suspended particles out. So it does a good job if you have a whole bunch of air leakage. At least the air is going to be nice and clean. So let's start at the basics. You have to have an air barrier that can withstand the loads put upon it. And we don't think too much of it, but they're actually pretty serious out there. And so we have 2 types of air barriers. We have air barriers that go on a substrate, and that's the majority of them. That's a fluid applied or self-adhered or spray foam, and we're putting them on an OSB, a plywood, CMU, whatever it's out there. And we don't have to worry about the structure side because that's already done by your wind engineer and so on. So as long as you can get the material on and have it stick, you can go home. The other ones are when they're part of the structure. Because an air barrier, the simple definition of air barrier is anything that stops air from going through it. And so extruded polystyrene, polyisocyanate, and so on, OSB, plywood, can be part of the structure. So we've had air barrier materials in our buildings all the time. We just haven't made them into an assembly and into a system. The second thing you need to be concerned about is the loading I mentioned. So if you take a look at this line here, ASTM E2357, that's a test that we do in air barrier assemblies, 8 foot by 8 foot wall, it's got penetrations, windows. And we tested up to 600, 800, and 1200, slightly different numbers. And everybody feels that's way over numbers. But those numbers come from the wind and the loads that are going on our building. But what most people don't realize is that's for 3-story buildings and only 80% of the buildings in the United States. So depending where you are, and if you're going to have higher than 3 stories, you may need to have more pressure. Take a look at this. Boston's about 1,000 pascals in the 1 in 50 hourly wind pressure. If you go from a 3-story building to roughly a 400-foot high building, you went 5 times. Now you're getting down into about 5,500 pascals. So the whole point, there's a lot of pressure in our buildings, and we don't think about it because your structural engineers looked after all that for you. Even if you're using a material like extruded polystyrene or something as your air barrier material and your sheathing material, the fastening, the thickness, the spacing of your studs, that's all done. So normally you don't have to worry about that at all. Here's the biggest problem for people understanding. It's the difference between an air barrier and a vapor barrier. All materials have a water vapor transmission rate. All materials are vapor barrier. This table is an air barrier because if we test it, there's no air goes through it. But it's also a vapor barrier or a vapor retarder, whatever term that you want. And we changed the code a number of years ago, so there's no set number. We got class 1, class 2, class 3, and by default, class 4 is anything above class 3. So, but we get all hung up, and I have contractors calling me saying, you know, I couldn't get this material, I got to substitute it. The perm is 0.1 difference, but the architect says, no, I'm not going to allow it in my building. What we're talking about is drops of water per stud cavity per year. Like, who cares? But it's the biggest issue. So the simple definition is an air barrier stops air. A vapor barrier or vapor retarder reduces water vapor transmission rate. Really, really simple. However, as you'll see, there's 2 things that come up. Materials have all different rates, but a single material can do multiple layers. And then, even more complicated, depending on when you put that material that you're calling your vapor barrier in your wall, it's going to perform different. It's going to perform different than what it was tested to, and I'll go through that too. So, and here's what I'm talking about in the difference of water resistance. Look at these last 3 lines. This all comes from our website. All I did is I went on the website, I looked at all the materials that ABBA have evaluated, and they have to report water vapor transmission rate in desiccant and water method. The code requires desiccant, but there's also a water one, and so we wanted to show both. Here's the reason why. Now this is a single material just tested in 2 different methods. First method, now these are in nanograms, not perms. There's 57 nanograms to a perm, so we're talking about less than 0.1 perm at 5 nanograms. That's exactly the same. Doesn't matter where you put that material, it's going to perform the same way. However, another material And these are all fluid applied materials, so it's not like we're comparing one type against another type, it's all the same. Take a look at this one. We go from 4.3 nanograms to over 2,000 nanograms. So if you believe you're putting a vapor barrier, vapor retarder, because that at 4.3 that's really, really tight, you put it in your building, but then it starts to perform as 50 perms, you got a completely different things. And now that's where the confusion comes in. But very basic, you got two different things that are happening there. So we have air barrier materials. A good example of an air barrier material would be OSB, plywood, gypsum, vapor faced, and so on. And then all materials, as I said, have different water vapor transmission rates. So all of them are vapor barriers, vapor retarders. You just have to put whatever class they're in. And a lot of them are going to fall into class 4. And then some of them are air barriers, vapor barriers, and water resistive barriers. Typical would be self-adhered membranes, your fluid applied membranes, spray foam. A good chunk of what we would classify as air barrier materials would also be water resistive barrier materials. The only thing I can think of at the top of my head is not water resistive would be gypsum faced, paper faced gypsum. You're never going to put that on the outside of your building. Now, then you can get into an air barrier, a vapor barrier, a water resistive barrier, and a heat barrier or insulation. And that would be something like cellular plastic. So that's polyisocyanate, that's extruded polystyrene, that's spray polyurethane foam, closed cell, and so on. So you've got all those materials, and they can all do those control layers. But was it designed for that? Was your exterior sheathing designed to be also your water resistive barrier? So you've got a whole bunch of these materials in your wall that can be classified one of them, but if you don't use it in that way, it doesn't make any difference. So let's take a look at what we're seeing in the field. So what we've covered so far is you got a whole bunch of air barrier materials out there. They got different water vapor transmission rates. They're going to have different heat barriers in some of them and so on. They're all going to perform differently. But let's get into what we're really talking about is how do you properly install them. The Air Barrier Association was started in 2001 in Boston, Massachusetts. And it was a response for the Commonwealth putting a requirement for air barriers into buildings. And everybody was all excited, you know, this is a great day and so on. And then somebody said, who's going to install it? And everybody looked at each other and go, we got a problem. And so the result was an association formed. And so we do training and certification air barrier installers for the last 22 years. What do we see? So when you're looking at installation of air barriers, you're looking at these things. What is the environmental condition? What is your substrate need to be done right? And then we're going to talk about self-adhered, fluid applied, spray foam, board stock, and commercial building wrap. Those are the most common air barrier materials that are on the market today. So let's go through the general environment. So what we're talking about here is you walk on the construction site this morning, you're going to install the air barriers. If it's pouring rain, obviously you're not going to do anything in installing. But it gets into even a little bit more details. So depending on your material, there's going to be limits. How cold, how hot it can be before you can install it. And they're going to be different, depends on a fluid applied versus a self-adhered one versus spray foam and so on. And even if the ambient temperature, you know, you get from the radio, it's 73 degrees today, you also have to look at the substrate temperature because it can be different. If you have the sun shining on one side of your building, it's going to be extremely hot. If you're in a cooler climate, the north side of the building could be very cold. And it's not just the ambient temperatures, but the substrate temperatures are really critical as to when you can install them and not install them. So one of the things that we require is you install the material is you do a point and shoot thermometer. And you need a relatively good quality one. It doesn't have to be thousands of dollars, but if you pay $10 for it, it's not going to work. And so you have to check the substrate to make sure that it's not too hot, not too cold, and differences on there. We also want to know the relative humidity. What is the percentage of moisture that's in the air? And the reason why, especially when you get into fluid applieds, some of those fluid applied materials will react with the amount of moisture that's in the air. Spray polyurethane foam, it reacts with water. So if there's a high relative humidity, it's going to affect how the foam foams up on the building and things. So you got to check the ambient temperature, you got to check the substrate temperature, and the relative humidity. If what you're spraying on isn't acceptable, it's going to be hard, or even so. I've been told, this is a picture we got somebody years ago. This is a backup wall with a brick veneer in front of it when the brick veneer came off, and I've been told it's not been photoshopped. So what would you do if you showed up in the job site and you're supposed to install, and I don't care what type of the air barrier is, what would you do? Now this is extreme, but kind of along the line that we have. And there's always ways that you can do it. This is not structural, so it was just sort of thrown together. I suggest it was a Friday afternoon before a long weekend or a Tuesday morning after a long weekend that they put this in. And there is a way that you could fix that if you wanted to go down that road. But the only material I could figure out that you could use would be medium density closed tail foam, and you basically foam over everything, fill the gaps and so on. And we did have a school in New York when the brick veneer came off, the substrate was terrible, it wasn't this bad, and to redo the backup wall was too expensive. And so the school board didn't know what they're going to do, and the answer was we could put spray foam all over it. That would give us a relatively smooth surface, and because it's going to have a brick veneer a couple of inches in front of it, it wasn't bad. You don't really want to go down that road. You want the substrate properly prepared on it. There's only 4 requirements. They're pretty simple: clean, smooth, dry, and sound. So clean, can be anything from dirt to water to dust to mortar droppings, whatever it is, because you want your material to stick to the substrate, and if you have even dirt and dust on there, it's going to stick to the dust and not to your substrate. And what we mean by dry, a lot of the products react with water, plus it's a bond breaker. You try and put a piece of peel and stick on a wall that's wet, it's going to fall off before you even walk away. What we talk about is smooth, is depending on the material, and especially if you get to very thin fluid applieds, you have to have almost like an interior finish, because a very thin fluid applied membrane can't bridge very wide gaps and so on. If you're using a thicker material, if you're using self-adhere that comes in sheets, it's got a little bit more forgiving on there. And then it needs to be structurally sound. As I mentioned earlier, most of the time we rely on the building to provide the structural strength, and we just have to stick it to the wall. But we've got to make sure it's stuck to the wall, and I'm going to cover what we need to do there too. This is a project I was on, and the air barrier installer. Now you got to keep in mind, your job as an air barrier installer is to make it completely airtight. So you want to connect materials. You can connect a roofing material to a wall material, to a foundation, waterproofing system, and so on. But you got to make those connections. And how would you do it? You got a roofing material up here, you got plywood here, you got steel framing here, you got structural steel, and down here you got gypsum board. That's a bit of a nightmare. And it took a while to figure out how to actually make all those connections. Here's the same project. You're trying to have a nice smooth wall, and if you're putting obviously a fluid applied here, these gaps are too big to span. Steel's an air barrier, so that's not a problem, but how do you fit in there? If you're trying to put a sheet good and this is sticking out a couple of inches, it's just not going to work. There's always ways to handle that. If you have a big mess like that, sometimes the easiest thing to do is bend sheet metal to go over top of it. Sheet metal is an air barrier, and you connect fluid applied or self-adhered or whatever you have on the sides there. Ways of doing it. Earlier I mentioned the dry part of it. So masonry, obviously there's a lot of water here. a lot of moisture in it. We use moisture meters to tile. To be honest though, we still haven't figured out what's an acceptable substrate for moisture content. We get a lot of calls on gypsum. When do I not install in gypsum? When is the core, the amount of moisture in the core too much? Because we see cases where the facing actually literally comes off and so on. And we're working on that as a research project. We have some guidelines, but right now we can't say definitively. There's tests for CMU. It's actually a really simple test and easy to do. And you don't need any equipment. You need a piece of poly or a piece of foil or something, and you simply tape it over your CMU, leave it overnight, you come back, pull it off. Is it dry or is it wet? If the moisture in the block itself is quite high, you're going to see that all wet. What you can't see behind it is the same amount of moisture is coming through there, but it evaporates so fast you don't really see it. This is all covered in a 3-day training program that we go through. And then the other thing that we run into, and this is a big issue, the general contractor wants everything going, and so the air barrier contractor gets called out, you know, get the air barrier in the wall today. If you don't do it today, you're fired, or I won't pay you, and so on. But when you look up, they haven't even finished the second, third, fourth floor, and there's no roof on the building. And there was one, probably the most serious one, school was being built with CMU, and the contractor, the general contractor made the trade contract, put the air barrier all around the building, and then we had a really heavy rain, which created a swimming pool inside the school. And of course the lawsuit started, and so the water stayed in there quite some time because everybody was fighting, and it literally pushed the air barrier material off the wall. So the day it was installed, it was absolutely perfect, but within about 2.5 weeks, it was laying on the ground. So moisture, not only on the surface, which is a bond breaker, it'll come off, but moisture in the substrate is a big issue, and we're working, trying to give guidance to our contractors out there. You also have a lot of issues. We had a research committee meeting this morning, and one of the issues is how do we connect to fireproofing? Do you put the air barrier over top of the fireproofing, you put the air barrier on, and the fireproofing goes over top? Do you keep the two separate? Do you have to have a transition and some sort of steel between the two of them? What do you do? And our contractors are asking for guidance on there. Typically, you cannot touch fireproofing. That's been an engineered system, and so you don't want to get in there. Air barrier materials don't stick to fireproofing, even the cementitious one. And so we're trying to deal with that. Right now what happens, the air barrier contractor typically comes up to the fireproofing but not over it. And then efflorescence, this is minerals inside concrete. And when you have moisture in that concrete or CMU, the moisture comes out and evaporates, and it leaves the salts that it's picked up within the CMU. Again, that's a bond breaker. That's almost like a powder. So if you try and stick something to it, it just doesn't work. And then you can see gaps. This is a steel column, and so you don't necessarily put your CMU right up to it. You could have control joints. You could have other things that are fairly big gaps that you can't just spray over it or put self-adhered over. Exterior gypsum, it's got to be clean, dry, and generally you need to prime it. So in this particular case, we get a lot of calls, as I mentioned, about, you know, we did a pull test on it and the facer came off. Is that good or bad? And it depends really on the project there. It needs to be clean. It needs to be primed. And if you have a product that has a glass facing, you're going to have to put 2 layers of primer on, because the first layer is going to be sucked into the material and it's not going to be enough to attach the material. So you have to put a second layer on. Why don't you do just one single thick one? That doesn't work, because the primer will not cure fast enough and so on. So you need 2 thins. So if you're coating on that job, you got to coat, even though the material overall will be the same thickness, you got to coat, you got to go back twice. You don't necessarily have that with other substrates, OSB, plywood, and so on, but glass face gypsum is a big issue there. The other thing we run into a lot of times is the contractor that's putting the exterior sheathing on the gypsum is they don't necessarily do it that well. Plus our buildings themselves are not perfectly square and true and everything. So you're going to have gaps. Not necessarily anything wrong with them. But again, your gaps, if they get too wide, have to be treated. And it could be as simple as filling it with a caulking compound, or you may have to put what we call a transition membrane over that area. Because any air barrier material that is fluid applied or self-adhered and so on only will span a maximum gap, and then you have to do reinforcing there. Poured concrete is an air barrier, so technically you don't have to do anything to it. However, it's not monolithic, and so you're going to have control joints. You're going to have between the concrete opening to a window, a door. You could have structural steel coming through the concrete, whatever it is, and that's what you need to do, at least your transition membranes. And a lot of times you'd have, in this case, like a poured floor, it's going over top of CMU, so you could cover 2 inches of the concrete floor and go home, but it's probably easier just to run the whole thing there, because you got to take it up the walls there too. We do have moisture meters that can tell you the moisture content of wood-based products and gypsum-based products. When we get into CMU and concrete, it's pretty tough. There is moisture meters for concrete, and you can get the pins that you literally hammer into concrete. But again, whatever you're going into, a 1/2 inch, 1/4 inch, you're only measuring the moisture content there. Do not be confused with the 28 days that's talked about with concrete. It cures it in 28 days. True. Has nothing to do with moisture content, all to do with strength. And so after 14 days and after 28 days, there's 2 numbers for compressive strength that will tell you whether the concrete is cured. But it could still be filled with water. And if you are, especially on the south side, with you got the sun, if you got moisture in the concrete or any substrate, but concrete's bad, you put your material on, you've checked it, you do everything right, everything looks good, the sun comes out. Building science says moisture transports from wet to dry and from hot to cold. And so that moisture that's in the concrete is brought out to the surface underneath your air barrier material that you installed, and now you start to get blistering. And that can happen a week after, 2 weeks after, whatever is out there. And again, in poured concrete, you don't necessarily have a problem, but we have what we call bug holes and cracks in the concrete and so on. And in this case, you have sort of honeycombing in there too. You got slurry, kind of hard to see it, but this is the wet gray water, if you want to look at it that way, but it contains the cement in it running down. All those things are going to affect installation. So if you're an air barrier contractor, the one thing that you have to do is make sure that the general contractors knows what you need for the substrate. Do not make it your job. And do not try and fix the other person's. You got to go on the job site, you got to make sure it's acceptable. If it's not acceptable, go to the project manager, the general contractor, get that trade to come back and fix it up. But more importantly, make sure if you're bidding on that job that there is in the contract documents who's responsible to make sure the substrate's proper. Because it can be a big job if you try and take it on yourself. And then the other thing with poured in place contract, the forms that they use are expensive. And to make sure that they can reuse them and they don't get stuck into place, they lather the oil on them. And that oil is left there. If it's fairly new, you can use soap and water or something like that and wash it down. Over time, that oil will dissipate and so on, but it'll affect your adhesion. Oil is a bond breaker. It's covered with oil, no way it's going to stick there. Wood is a little bit different, but you got the same type of issues. In this case, the gap is too wide. They're putting a backer rod in there. That's your backing for your air barrier material, so that's good. Any roughness that's on there, any gaps, whether it's wood or gypsum, if there's holes, there's gaps, there's damage, you got to cut that out and replace it. But that's pretty straightforward there. Now let's get into the materials themselves. So if you go back in history, The first air barriers that were installed on walls was roofing material, torch on. And somebody, when we started realizing we needed air barriers on the walls, they go, well, we torch it on the roof, why don't we torch it on the walls? And this is on a CMU. And that was used back in the 50s, 60s, 70s. And somebody came along and said, well, rather than using flame on the construction site and torch on, you got to melt it to get it installed, why don't we pre-manufacture? And that's what happened when we got what we now call self-adhered asphalt-based membranes. It's an asphalt on a polyethylene carrier sheet, and we put it on the wall because it's already sticky, go home, almost. So you need overlapping of seams. You have to shingle things. It's a minimum of 2-inch overlaps on all your seams there. And same thing with your vertical joints, you have to have overlaps. The big issue with all air barrier installation isn't a flat wall. Almost anybody can do that. It's what do you do when it comes to a door, window, a pipe, electrical outlet, a crack, whatever it might be, and that's the detailing. If you sort of think, if you've ever painted your own home or something, where's all the work? The work is in preparing it to put the paint on. Once you have all the substrate done really good and you've cut in the corners and everything, then to slap the paint on is the easiest job you can do. Same thing with air barriers. You got to fix up all these issues, make sure you have the overlap, put transition membranes, in this case around a pipe. This is part of our training. This is a transition membrane from a wall to a foundation. You can see some of the gaps that has to be covered in this one. How are you going to do that? So you got to do that, and it doesn't matter if you're using self-adhered or fluid applied or other things. That's all your preparatory work. Once that's all done, whether you're going to spray it on or you're going to put sheets on, becomes really, really easy. Some of the requirements that you have, this is really, really important. Every manufacturer, self-adhered material will tell you, some of them require primers. If the asphalt based, you're going to do the priming on any substrate, not just gypsum, and then put your material on. Some of the new, what we call polymeric sort of based is you don't need a primer, but it doesn't matter whether it's those two, you have to roll them. And we're not talking about you taking 2 fingers and rolling back and forth. We're talking about you got to get in there and you put some weight behind it. And there's special rollers out there, it's 2-handled, and you really need the 2 handles to get in. If you don't do that, your material is not going to stick properly. And if you did a really, really bad job, you come back 2 weeks later, the material could be literally on the ground. And then you have to overlap your seams. We talked about that, but in this case, we wrapped it into a window. The other thing is every cut edge. So if you cut a material and that's left open like you see here, you've got to run a bead of mastic to seal that off. If you just simply overlap your material and you haven't cut it, you don't have to do anything there. A lot of times self-adhered over the years have been used as your transition flashings. So you put it into your windows, you put it around your penetrations and so on. The new products out, there's a lot of what we call liquid flashing. It's like a big caulking gun, you caulk it all over, even a window, and then you take your putty knife and you just smear it off. A lot easier, a lot to do and so on. So we see more and more of that coming down there. Here's the types of things you don't do. Here's what happens when you put a self-adhered material against a roofing material that's not compatible. It comes apart. It's not properly adhered. You can see the wrinkles here. This was not even cleaned in this case, just went over top. And you can see here, first of all, you see no primer. This material needs a primer. It's not been rolled, and now you get the mortar squeezes that is going to create tents. Go back to the wind forces and so on. If you have a tent, that gives you a little pocket. And over time, as you get the pressures on your building, that's going to work back and forth, and eventually it's going to start peeling off your wall. So let's switch to fluid applied. Fluid applied is the most common one I see out there now. And the reason why it's most common is you can do more square feet per day. So if you're trying to do what we call thermal fusible, which is not used in the United States because of open flame on the construction site, you got maybe 50 to 100 square feet per day, somewhere in that range. If you went to the self-adhered, you got 4 times. If you go to fluid applied, typically you have 4 times better too. But keep in mind, you still got to do all the detailing. Doesn't matter what the material you're putting on. Once you got all that detailing done, then it becomes very quick. Again, over a flat wall. But if your all wall is covered with penetrations and doors and windows, then not sure if fluid applied is going to help you. But there is some things that we look for. So here's an example. And again, as I mentioned earlier, depending on the fluid applied material, they need to be really smooth. In this particular case, even the cracks between the gypsum boards need to be treated. Not a problem. We are very easy to do, but it's another step. You can see they've done it around the windows. They got the transition membranes. See here, they sealed around basically a structural impact here. And then when you're all done, you come back and spray it on. Now, fluid applied has more restrictive temperature limitations than self-adhered. So it depends. And fluid applied can come on in 1 component, 2 components, cold spray, hot applied, cold applied, and so on. So it's all over the map. You have to really look at what the manufacturer wants you to do. The types of things that we see again is not proper preparation. It's probably hard for you to see, but this was a material that's put on and then a sudden rainstorm came in. And this is back down to the transition membranes. And it's kind of hard to see, but the material is actually slumping down here and down there. So some of the materials are water-based. We don't see too many solvent-based just because of the regulations on off-gassing. And so you've got to really understand the material. This can be fixed, but it's a lot of work to go back and redo everything. Here's a good job of preparing the substrate. They did all the joints for this particular one. This is a change in substrate, so that needs to be covered with a transition membrane, at least 3 inches on each side. And there's some cases where spraying is not a good idea. Any idea when spraying is not a good idea? I'll give you one example. This was up to Alaska. They were working on this building, and there was overspray on 12 cop cars. So no argument from the contractor. He just went and repainted all 12 on there. So you can see in the background, this is downtown somewhere, and he's using a hand roller, and you wonder why. That's still a lot cheaper than having to pay for overspray. Types of things that we see, here's where it didn't adhere to the transition material, so there's a problem. And it's generally a problem with the material that's being sprayed on. Here's what we have is cratering and pinholes. This could be a number of things, even simply it's been left exposed too long. All materials have an exposure time, and after that exposure time, it starts to really work on the material. And here's again a bunch of cratering. We've also found issues with CMU. When you're spraying on them, you get what is called pinholes. It's literally a hole in the material. And the short answer is you go back and spray some more. But in central, if you come from central United States, we have an issue there. We believe it's how they make the CMU and what they put in the CMU, that every time we put it on, pinholes, put some more on, more pinholes, put some more on, more pinholes. We haven't solved that yet. But and it happens nowhere else in the United States. So we believe that that manufacturer is putting something into the mix, and there's no restriction on the manufacturer of CMU can do whatever they want as long as they get the strength. But we haven't figured that out on there. Thickness, because you're spraying, so it's going to be the person that's spraying that day and how cautious they are to do the proper thickness. Obviously, if it's too little, it's a big issue because you don't have all the properties, but too much can be a problem too. And you can see here it's not really covered. You got gaps here. They've got blisters. It's kind of hard to see down there, and blisters up there, and actually water dripping down here. Now there is some fluid applied materials that use waters as a co-spray. So in some cases, this is not bad. This is always bad. This can be okay. These blisters can weep, as we call them, and it's the way the material is done. So the water is used to help get everything on the wall, carry the material in the wall, and then the water actually leaves the material, drains down the wall, dries up, everything's good. Other materials, if you get this type of things, it's going to be a problem. So you got to, again, go back to understand that. This gets back to the sprayer. We call those shadowing. You're always supposed to spray 90 degrees to whatever. You're not supposed to go like this. In this case, they sprayed down, so now you got a shadow. There's no material here. This is a major air leak. This you got pinholes. These are actually bigger than pinholes. And then you got a whole bunch of material that's just sliding down. Again, pinholes here. If they're big ones and so on, we call them fish eyes. Again, you got to fix it. You can't just walk away. Here again is more ideas of what we call cratering. So this looks like a mini crater that's on the moon. So they sprayed the material, then a piece of solid material comes through your pump and your lines and out your gun, hits that fluid applied, and it creates that little crater. Again, it's got to be fixed. This is cracking, too much UV. Here's one of the reasons why you get cratered. Most of the materials react to air and relative humidity in the air. And so this drum has been left open and it's actually solidified. Some of that can get through the lines and create the problem. So you got to handle and store your material properly, but this basically that's a wasted drum. Here's where you put too much on. You can see it slumping down here. We also got some discolorations, but you can see it sagging, all these cases sagging down here. That's too much material too fast. Hasn't allowed, sometimes you have to do 2 layers because the overall thickness is maybe 40 mils or 50 mils. So you can't necessarily put that on in one spray, but you got to let the first side cure on there. Improper thickness, if you're spraying, you use what is called a wet mill gauge. As you're spraying, you should have that in your other hand, so you're always checking. Really simple, these are notches. You stick it into the wet material, you look for the last one before there's nothing on these little notches that you have on there. So it's really easy to do, and you should be checking that every square feet as you're spraying. After it's cured, it becomes more of a problem. Sometimes the bottom line is you got to take the material off the substrate. So now it's a destructive test. And you look at the edge of that material and how thick is it? Well, first of all, problem number 1, it's not easy to get off. And then problem number 2 is how do you test it? Well, you can use a caliper or a gauge, and you can do the thickness. Use a digital one because they're much more accurate. This is called an optical comparator, and it's like an eyepiece. And it's got these little notches, and you hold the material up there and you turn it until the notches just fits right over the material, and you know how thick it is. We're working on ultrasonic. The ultrasonic machines that you buy for $300 or $400 don't work. We've got one for about $2,000. Seems to be worthwhile, and we're doing some research so we can go back to our contractors and say, rather than spending all this time and then you got to go back and repair it, use an ultrasonic, and it's reasonably accurate there. Spray foam can cover a whole multitude of problems, but spray foam is very important of the installer because it's the installer that's actually manufacturing the product. The supplier sends you 2 chemicals, one's called a resin, the other one's called an iso. Your job is to heat that material, put it under pressure, spray it on the wall, and make sure that it has the material properties. Also, during that time period, safety is absolutely critical. ABBA requires in any organization that is safety conscious, if you're spraying or in the spraying area, 100% mask, full face mask, positively supplied fresh air, gloves, everything. You shouldn't eat it, wear it, drink it, anything. It's not a good chemical. Once it goes on the wall, it's combined with the iso and the resin, goes on the wall. In about 2 hours, it's inert. Won't have any problems. But you also can't have any other trades. So you got to warn people to stay out. There's a whole list of things you have to do. If you go through all that, it's actually a pretty good material. In this case, they've done the transition membranes around the windows. Nice flat wall, easy to do. Thickness, again, is an issue. As you're spraying, you can't really tell. Now, you can't use a wet mill gauge, but what people do is use a rod, could be a welding rod, and they put tape around what thickness you want, 2 inches, 2.5, 3, and they have it in their hand, and as they're spraying, they just, do I have to touch up a little bit there? So not having enough thickness is probably the number one you see out there, and then improper substrate. Here's the types of things you see, part of the health and safety. Your chemical drums have to be in the truck. You got to have fire extinguishers. You have to have safety kits. You have to have eye washes. Here's what we call a proportioner. Comes out of 2 sides on heated hoses out to your gun, and the 2 chemicals come from each side, swirl together and sprayed on the wall. Anything that you change, temperatures, pressures, temperature of the liquid, have you not kept your lines clean? There's filters down here, mesh screens, there's filters here. They can become clogged or partially clogged, and you stop the amount of material that's coming out of one side. They're supposed to be 1-to-1, so one could get a little bit else. We call that off-ratio foam, and if you spray it on the wall, you're going to be taking it off the wall. Lots of things to do, but as I say, if you go through it, it's a good material. You have the same requirements for spray foam as anything else. You can see the transition membranes about windows, between the wall and the foundation down here, and then you can go ahead and spray the walls, no problem at all. Same type of thing, here's shadowing with spray foam, no difference than fluid applied, it's been sprayed this way. This is a big hole right in through the substrate. This particular, I was in a very hot area, and it was really hard to spray without being overheated. Outside temperature was about 120 degrees, so it took them a lot of time. They had to put it on very thin layers on there. Here's a measurement. It's a very fine pin that goes in. It doesn't really create a problem with the foam. You can find out how thick the foam is and go. And again, here's some things not to do. Brick ties hasn't been done. They haven't actually taken it up there. And you can also get two thickness of foam. You can say, well, you asked for 3 inches, I gave you 4, you should be happy. But if it's going to cover up the airspace that you need behind brick or other materials that's going to be on, if you have to ever shave spray foam off or take spray foam off, you don't want to ever do it again because it's really, really tough. Adhesion, same thing with any adhesively attached. Here's cases where it hasn't bonded to the substrate and it is literally popped off. Another case being popped off, and isocyanate, which is doesn't like water at all. They fight each other. So if there's any moisture whatsoever, either on the surface or in the substrate, in the heat of that material will draw the moisture out. You get really big bubbles, and it's really, really easy to take off. So, and then if you're spraying different layers, then you have what we call cohesion. You want one layer to seal to the other. Just again, not spraying it right. Here's what we see when we call it off ratio. So one is going to be colored generally by the manufacturer. That's a resin side. The other one is isocyanate. It's always going to be sort of a brownish color. So in this case, we call this resin rich, and you can see it's not good foams all over there. And you can't fix it. You got to pull it off the wall, which is not a nice job. If you spray too fast and too thick, and most foams has a maximum lift if 2 inches. So if you need to put 4 inches, you got to spray 2 inches, let it cool down, come back, spray the other 2. If you spray it too fast, too thick, you get what we call thermal cracking, and it actually splits. Okay. The worst thermal cracking I've seen was on Syracuse University. They did it's called the Energy Center. The contractor was asked by the general contractor to spray when it was too cold. It's in November. If you've ever been to Syracuse in November, it's not hot. And so they sprayed it was sprayed from the inside between the studs. It was cold, there was a little bit of frost on the wall, so no adhesion. And when they sprayed, the stud cavity is 16 inches wide. When I saw the foam, if it was 6 inches wide, I'd be surprised. That's how bad it can shrink, if not properly done. Foam needs something to grab onto. It grabs onto and won't let go. If you ever get it on your clothes, ever get it on you, you're not getting it off. You'll wear it off. But it needs to track on there. In this case, with a little bit of water and steel studs, it had nothing to grab onto. Plus, it was beyond the limitations, so it literally shrunk. I'm dealing with one contractor right now. He's put up precast panels, and they sprayed foam in between it to do the sealing on there, and the foam has actually moved the precast panel. So we're talking about some serious. Do a right job, no problem. Look after everything. Here's an example of this case where there's water. You can see that we're looking for really nice, small, you shouldn't see anything like this in the cell structure. It should be all nice and small. This is where you got a bad situation. Again, here's good foam, but here it's reacted, probably water on the substrate. And you can walk up and pull that off, whereas otherwise, with a sledgehammer and chisels and everything, it's really hard to get foam off the wall. Here's what happens when you do it too thick and so on. And I'm guessing this is the first time a guy sprayed, but I have seen worse. You get a really good sprayer, it's really hard to tell that there's anything below there. Everything else, when you see something like that. So, thickness, this job, it was literally the guy's first day on the job. The guy phoned in sick. The contractor sent out somebody who's never sprayed before. Requirement of the job was 2 inches. That's 8.5 inches before you hit the brick tie. So that all has to be shaved off, waste of money, waste of time, and so on and so forth. And something's wrong with the machine when you see foam like this. I got a call from one of our contractors, said, I know you talk about foam a lot, and what I look here, I think you said it's not good. Sent me pictures, and I go, no, there's something wrong. And I says, give me pictures. So take pictures of the equipment, take pictures of the substrates, whatever. I'm looking at the picture of the equipment, and remember I said you need heat and pressure? And I look at the heat, it's not on. You have to raise the temperature to about 160 degrees of the material before you can spray it. So, and this is a contractor sprayed for years. I said to the inspector, go over to the contractor, tell him turn the heat on, wait for about a half an hour, start to spray, and then send me another picture. Sent me another picture, the temperature was up to about 155 degrees, and when he sprayed the foam, beautiful. So something just as simple, you forget to flip a switch. Insulating board stock, there's not a whole lot of difference between what we call insulated board stock and non-insulated. This is stuff that is sheets of something. And insulating board stock typically be extruded polystyrene, polyisocyanate, those type of things. And uninsulated is going to be your OSB, plywood, those type of things. That's all done in the factory. So when you get out to the job site, then it becomes a matter of putting the pieces together. So one of the advantages of any mechanically material is you're not subject to the substrate issues. If it's a little bit of water on the substrate, not a big deal. If it's misting outside, not necessarily a big deal. So there's some advantage to mechanically fastening because you're not dealing with all the issues you have to deal with anything that has to be stuck. All you got to do is put your fasteners. You do need fasteners at a certain pattern. These are 2-inch diameter plastic headed nails, and they're typically spaced 16 inches by 12 inches, 16 inches by 16 inches, and so on. So that becomes a lot easier to look after and do, but you still got to come back and make it sealed. So all your joints that you have to have transition membranes, It's a little bit harder now to use these materials to connect them to doors and windows and pipes and so on, because you've got to do the same thing as you would with anything else that's out there. But it can be done. It can be a really good job. Some people like board stock versus fluid applied versus self-adhered. It's also giving you, this is one of the materials that is an air barrier, vapor barrier, water resistive barrier, and a heat barrier, all four in one. Non-insulating, this happens to be a gypsum-based material with a membrane installed in the factory. There's other materials on the market that are OSB-based and they have a fluid applied sprayed on the factory. The advantage of those materials is that's done in a controlled space in the factory. And so those sheets, 4x8 sheets or whatever size, are shipped. You have to fasten them and you don't have to worry about putting the air barrier on. You still got to do all the transitions, and now you got to deal with every fastening that's on there. It does have some advantages that you can, again, because it's mechanically fastened, it doesn't matter the temperature. And when you're putting the transition membranes in, but you can keep a lot of moisture out by just simply having those on. And you have to wait a day or two until it's completely dry to go back and do the joints. Same type of issues on there. Here's a factory bonded. This is a spray-on one on there. Here's an example. Types of things, again, your sheets don't necessarily line up, that are nice and tight. You got to deal with that, and then you got to fill all the joints and fill all the fastening holes out there. Commercial building wrap. This is material, something like Typar, Tyvek. There's about, I don't know, a dozen materials on the market. Be a little bit cautious because some of those some people call them house wraps and so on, stucco wraps, and some of the materials are water resistive barrier, but they're not an air barrier because the air leakage is greater than what is allowed. And there is the same manufacturer, but gives you a little bit heavier material, and now it becomes an air barrier and water resistive barrier. They're going to be highly vapor permeable. Typically they're between 10 and 30 perms, and the idea is so that they can let water vapor out. So if there's some moisture in your walls, they can dry out. Great idea. However, keep in mind, moisture doesn't know which way it's going. It always goes from wet to dry. So as an example, in Las Vegas here, if you had a big rainstorm right now, and you got this material on the outside of the building and the sun comes out, that moisture is going to be driven into your wall. So I dealt with Title 24 in California because one manufacturer wanted to raise the minimum requirements of 10 perms to 30 perms because that's what they manufactured. And I says, well, great idea. However, it rains in California. You got a lot of stucco, which we call reservoir cladding, holds water. After a rainstorm, when I'm in California, generally the sun comes out, beautiful day, that sunshine is going to push all that moisture into your wall. So you got to decide. And they decided not to go to 30 perms. And there's some cases where even where the code would allow you to do and encourage you to do a very high vapor permeable, let's let the building dry out. There's a lot of building owners and designers going, well, that's a great idea, but I don't want the water come in. So they use a very low water vapor transmission rate material. All gets into the type of building that you're going to do. Easy to put on. Again, your 2-inch diameter plastic headed nails because you don't want them to rip the material. You got to tape all the seams. You got to still do all your transition membranes, connect to your doors and windows, connect to your foundation, and so on. And that's what's going to take some time. The one advantage of this type of material, typically you can get it in 12 or 14-foot rolls. So if you have a single-story building, you can walk around the building and it's all one sheet. If you have 2 or 3-story buildings, at least they'll cover each story one at a time. The types of things that you shouldn't do, if you see somebody stapling, that is no longer an air barrier. That's a water resistive barrier only. Nothing wrong with that, but as a water resistive barrier only, you just want to tack it in place because all it does is shed the water. As an air barrier, it's got to withstand that pressure. So that's a 2-inch plastic headed nail, 16 by 12 or 16 by 16. You also got to watch for anything that's underneath. If you have something that's protruding, that material is going to move. Wind's going to affect it. And that's going to rub on whatever's protruding, and sooner or later it's going to wear its way through there. And we see a lot of damage after installation because it's been installed as a water-resistant barrier, or at least I hope that's what they put it on, because it doesn't meet the requirements of an air barrier. Wind comes along because it's stapled, a little piece comes off, and I've seen buildings where it's literally just hanging. It's not covering the wall already. So now you've got to go back and fix those things up. So proper installation, even if you're only using it as a water-resistant barrier, is still the way to go. So I mentioned at the start that if you are using a material that goes on a substrate.
Greetings from the deck.
So I mentioned earlier, a lot of times the substrate is giving you all your structural part, and so the only thing we have to be concerned about is in making sure it's properly stuck. I've told you all the things that could cause it not to stick. Dust, moisture, everything on there. So one of the tests that we require from the manufacturer to perform and for the installer to perform every day to make sure it's properly stuck is a pull adhesion test. I'll walk you through that. There's two different manufacturers, but basically it's portable. You take it and you can determine the adhesion rate of the material. You basically have a puck. This can be steel or it can be wood, as you see here. You glue it on the wall and you put the material, the pull tester over top, and you basically hand crank it. And there's a gauge on there. We require a digital gauge. It'll go up and tell you what is the force that's required to pull it off. You always pull to failure. It doesn't mean that the material's failed. You just want it right off the job. We started off referencing D4541. I'm not going to get into a lot of detail, but you could see those in a project spec, do the pull test according to 4541. ABBA always modified that, but people weren't doing the modifications, and so we developed our own specification, which is based on these two, and this is more realistic for an installer to do. It's free, it's on the website, you can download it. We teach it in our training course. And what we require is, we don't say anything's a failure, we just say where it's pulled off. Has it pulled the facer? Has it pulled the airborne material? Or is it separated at the glue level? And we require a set diameter and so on. All these things are designed to make it easier for the installer. We wondered whether the 16 PSI that we require is reasonable. We went through 3,600 reports on there, and you can see the numbers, but you don't see anything less than 1,600 or 16 PS on there. The other types of testing, I've just got a couple more slides, is to have air leakage. You can do, in these cases, we call them bag tests. You basically put 20 mil polyethylene, seal it to the wall, pressurize it, put a smoke bomb in there to see if you got any leaks. This is great for learning and for helping. We call it the bubble gun. This is about 24 inches in diameter. In this case, they want to know if the brick tie is sealed. You put a soap solution on, put this on, it draws pressure. If you've got a leak, you're going to see bubbles. You see bubbles, fix them. It's really that simple. Sometimes it's misused. Somebody will go into a construction site, well, you got a bubble. Got to redo the whole building. No, that's not right. This is really important. It's becoming more and more, and it's going to separate good installers from bad installers. This is what we call the whole building test, which we take a building and we pressurize it, and we're looking for a certain air leakage rate. It's becoming mandatory in more and more places. Washington State's had it for years, but now we're seeing it happening all over the United States. So that's something we're working on. We train and certify the people that operate this equipment, because you could have a false report. If the guy or girl that's conducting the test doesn't know what they're doing, they can say your building leaks too much, you got to go back and fix it. Or in reality, if the test was done right, you would have passed. So that's important to us to do it. We do a quality assurance program. Training and certification of installers is key, but we also follow up with standards and specs and inspections and so on there. So air barriers are pretty simple. They're any material that will stop air going through them. More importantly is making sure all the cracks and crevices and everything, connections are done. That's where we see air leakage. We don't necessarily see a problem with air going through the material. So it's the installer, how they put it on is what's going to make a good building or bad building. You can see that the substrate needs to be recritical, but we know what generally happens out there. We've watched it for 20 years. We teach you how to do that as you go through the training course. And if we see a building that has a problem, we know how to fix it. So you should never worry about, well, I made something wrong. No problem, let's go fix it. Let's get a good building. And finally, blower door testing, support it. It's going to separate good installers from bad installers. It's going to really help our industry there. And that's it.
Thank you.